Hi everyone, my name is Erick Cestari and I'll talk about differential fuzzing on Lightning Network. So I will first start with an example. So imagine if Alice wants to buy a coffee, and so Bob generated an invoice for Alice to pay. Bob is using any Lightning, another Lightning implementation made in C#, and Alice is using Rust Lightning. So when she tries to decode the invoice, it actually fails, and then Alice calls Carol to try to pay for her because she couldn't. And when Carol tries to decode the invoice and pay for it using another library implementation, using, for example, LND, so she could. So why this can happen today in Lightning? So we have currently differentially Lightning implementations, so it can cause some bad user experience if some Lightning implementation can decode an invoice and the others not, and they can behave differently, even trying to follow the same spec, which is the bolts. So by doing these tests, we can actually find some security issues, because if some implementation is doing more checks, for example, in the invoice and the others not, it can have caused some security issues. So to fix, for example, this bug, it would need some reactive fix, because we would have to try to decode the invoice in one implementation, then the other, and try to see which implementation gives an error and why it causing giving this error. So it would be nice if there is a way to systematically find these bugs between those implementations. So that's why one of the way of doing this is by using differential fuzzing. So first, who am I? My name is Erick Cestari, and I'm a 21 grantee, which is a non-profit organization that gives funding to Bitcoin developers. And I'm been contributing to Bitcoin Fuzz for like 8 months. And by doing differential fuzzing on Lightning, I could found more than 15 bugs across Lightning implementations, which we'll see some of those bugs. So in Bitcoin protocol, currently we don't have a specification for that, so we basically have to read the Bitcoin core code base and see how they implement that. So if you want to create a new Bitcoin node implementation, we would actually read the Bitcoin core code base and see how they do that. In Lightning, for the other way, we have a specification first approach. So we'll first specificate that in the bolts, which is the base of Lightning technology, and we'll discuss there what we want to change in the Lightning specification, and after that we will start to implementing in the Lightning implementations what is written in the bolts. So because of that, multiple implementations can follow this spec, but the specifications can be ambiguous or don't cover every edge case. So, for example, there is in the bolts 11, there is a case which the spec says that there are fields which contain one or more entries. So what happens if there is no entries? So some implementations like Rust Lightning and Core Lightning would reject that invoice, and others like LND and Declare would accept. So by doing differential fuzzing, we can explore those gaps and see where the implementations are diverging, and yeah. So let's first simple at first. So what is fuzzing? Fuzzing is basically a software testing technique which will provide random data or unspecified data to a program. So we'll show basically a diagram how fuzzing works. So we first start with the corpus, where will be saved the inputs that the fuzz will give to the program. So the inputs are sent to the fuzz engine that will take the inputs and mutate those and send to the fuzz target. The fuzz target is basically the middleware between the program and the fuzzer. So you get the data from the fuzz engine and use in the program. So we send to the program, and when executing the program, if we compile the program with coverage instrumentation to give some feedback back to the fuzzer, which we'll see more about that in the next slides. So by giving coverage feedback back to the fuzz engine, we know if the input could reach new path of code, and if it's reached new path of code, we'll basically save that because it's an important input that can give more coverage feedback, more feedback in the program. So we basically track every path of the code we executed. So the coverage instrumentation is we basically insert function calls when compiling the code that will give the feedback back to the fuzzer. So there is an example here of a C code, which is basically we send a int score and we make some if statements. And if we will compile that, so this is basically the high-level view of the compiled code in C without the coverage instrumentation. So it's basically the same as we saw before with the if statement and the else statement. So here is the code compiled with coverage instrumentation. So we can see that the coverage instrumentation adds that sanitize call trace guard function calls inside the final binary. So when executing the code, if it's reached that path, it will give the feedback to the fuzzer engine. So it will know that it executes that path of code. So let's see some example and run some fuzzing. So what is the problem with this double function? So basically, in this double function, we don't check about overflow, and this is a Rust code, and we'll basically do fuzz on that. So we have the fuzz target, which will give it to us the data from the fuzzer, which is basically bytes, and we'll consume that bytes to transform to a signed 32-bit number. So let's run this. Let me take here. So you can see that the fuzzer could easily find an input that crashes our program. So basically, if the input is bigger than the half of the max of the i32 value, it will crash because it will cause an overflow. So here we are using libfuzzer. So libfuzzer will give to us the corpus, which I talked before, which will have the inputs saved, and we have the artifacts that will give to us the inputs that could crash our program. So this is basically the binary that crashes the program. So this one, and let's see one more two examples. So if we fix that function to use, for example, a safe multiplication, in this case we are using checkmu, which is from the standard library. Let's see. Here. It's basically the same code. We see that the fuzzer will basically run forever because it will never crash because we are just multiplying, and we are just multiplying in a safer way, so it will never crash, and the fuzzer will run forever. And we can see some output that the fuzzer gives to us, like the coverage, which I talked about. So if the fuzzer basically don't increase this coverage here, it's basically because it's stuck, so it can't find new coverage path, new path in the code, because this is basically a simple code that there is no if statement, it's just multiplying by 2. So let's see one more example that can show us why giving back the coverage feedback to the fuzzer is important. So in this case, the application will only crash if we send a binary, a ASCII binary that is fuzz ln. So we have like this 6-byte sequence to crash our program. So let's run it here. You can see that the fuzzer gets longer to find the path, and it's basically find it. So here you can see the inputs being saved, and here in the logs we basically see that the coverage is increasing because it finds like the first ladder and the second and the third, and it will basically increasing the coverage feedback. So here in the inputs we can actually see here this one is didn't find any ladder. This one find the first ladder, so it's saved because it find a new path of execution in the code. This find the U, so just find like the other ladders. Here if we look in the inputs that crashes your program, it's basically fuzz ln, because the one this is the input that can crash our program. So yeah. So now let's talk about differential fuzzing, which is actually the theme of this talk. So differential fuzzing, we basically send the input to more than one program, and we'll basically then compare the outputs, so we can know if the programs are behaving differently. So if we take two functions that should do the same thing and they give different outputs, we know there is a problem in one of those functions. So here's basically a diagram of the differential fuzzing. We can see that it will take the input from the fuzz engine and then send to 3 different programs, and then we compare the outputs from those programs, and if they are all the same output, we'll basically, there is no issue, it's fine. We'll give the coverage feedback to the fuzz engine to create new inputs. And if they differ, we found a bug, so we'll crash the program, and then we can then replicate the bug by using the crash input. So this is an example of differential fuzzing. So we have the double function or double safe function, which is the check we're using the check move, and we have another double function which is safe, but it has a bug, basically off by 1, because instead of it is using x bigger or equal iter2 max divided by 2, but iter2 max is a valid value, because if you multiply by 2, it will give us the iter2 max, which is a valid value for a signed iter2 number. So if you do differential fuzzing in these two functions, we will find the input that will diverge, which is actually just 1, the iter2 max divided by 2. So let's run this differential fuzzing and see if they can find. So here you can actually see this one is the input, and the first function gives this value, and the other just return none. So this is actually the the value of the half of the arbitrary 2 max, and when multiplying by 2 in the double function, it returns the max value, and the other one return known. So we basically did the differential fuzz between those two functions, and we find where they diverge. And it's important to note that only doing fuzzing and in the first function and the second one, we would not get this crash because both are safe and will not overflow. And this one is more a semantic bug because the function is not doing what it should do. So I have been working on Bitcoin Fuzz, which is basically a framework for doing differential fuzzing in Bitcoin. So we do differential fuzzing in different libraries. We do in Bitcoin Core, LND, Core Lightning, and the objective of doing differential fuzz is basically find the bugs between those implementations. And so we have LND, Core Lightning, Rust Lightning, Eclair, and Lightning KMP. And we have some targets for these implementations. So it's centralized invoice, centralized offer in parse P2P Lightning message. So centralized invoice is basically receive a both 11 invoice and parse it, and then compare the outputs and see if they could parse it in the same way and took the same data from the invoice. And by doing differential fuzzing on Bitcoin, we could found more than 30 bugs so far, and we are find more and more. Just for the Lightning, we found more than 15. We have just those 3 targets. Yeah. So to make it work, we have to lead with different language. So, for example, LND is made in Go and Rust Lightning is made in Rust. So we basically have to compile then with coverage, with instrumentation, if possible, to give the coverage to the fuzzer engine. So this is an example of compiling the LND with cover instrumentation in Go, and the other one is in Rust, compiled with cover instrumentation also. So we have to work with interpreted or VM-based language tools. Basically, can't do compile with cover instrumentation because they aren't compiled language. So for example, Eclair that's made in Scala that use JVM, we need to be able to call the JVM inside the JVM the function. So this is basically the code in C++ that we first instantiate the JVM, and then we basically call the function inside the JVM and get the output from that. So let's break down a target in Bitcoin Fuzz. So to create a target in Bitcoin Fuzz, we just basically needs 3 things, and one is optional, but it can help us a lot during differential fuzzing, which is the target function, the input type, the output type, and the custom mutators if needed. So, for example, the centralized invoice target, the input type is both 11 invoice string. The output it's a string that contains all the invoice data concatenated. So the amount, description, the payment hash, etc. And the custom mutator is basically, we use a custom mutator in this one with the batch32 custom mutator, which we'll see more in the next slides. So for Rust Lightning, this is basically the code that integrates with the Bitcoin Fuzz. So we can see that we get the inputs as a C string, and then we parse it to Rust string, and then we send basically to to parse it to a bolt11 invoice, and then after parsing it, we start creating the outputs, and so we collect the hash, we collect the payment sequence, and so on, and then we return this string back to the Bitcoin fuzz to then compare between the others implementations. So LND we do the same, so we get the string, and we parse it using the library, and then we create the output to then compare. So and we have a custom mutator for this target, because bolt11 invoice has a well-defined encoding, which is the batch32, which has a checksum and has the batch32 encoding, which is just some characters, and we need to, when mutating the input, we need to maintain that encoding for the fuzzer not get stuck in basically creating valid checksum. So if we don't do that, the fuzzer will mutate the inputs and will basically never create a valid in bolt11 invoice, because it needs to create a valid checksum for the data, and it needs to be batch32 encoded. So what we do, we basically take the input, which is in the bolt11 format, and then we parse the batch32, and then we mutate the raw bytes, because we basically parse it through bytes, and then we mutate in that stage, and we encode back to batch32, and then we send to the target, which will have a valid checksum and be a valid encoding for bolt11 invoice. And at the end, we will basically compare the output. So we'll basically do a for loop, and we call the functions to serialize the invoice, and we compare the outputs. If they diverge, we found a discrepancy, and then we basically have a assert here to crash the program, and then we can replicate the bug by using the crash input. So let's run Bitcoin fuzz and do some differential fuzzing in real implementations. So here I basically will do differential fuzzing between LDK and core lightning. So first I will remove the custom mutator to see the fuzzer getting stuck in the coverage when it's good. So it will not create a valid invoice, and we can see here. So here we can see the coverage basically gets stuck in 600, and it's hardly can getting more than that. And now let's compile with the custom mutator to see. So it's increased a lot, because now it's creating a valid bolt11 invoice, and it is sending to the core lightning the same input and the same input for the Rust lightning. So, and then we are comparing the outputs, and I have here one input that can crash, so they will diverge in that input. So let me execute that. So it crashed because I used an input that they diverge. So here you can see the logs. So core lightning could parse the invoice, and here are all the data information inside the invoice. And in LDK we didn't get result, but we got an error, which is a invalid signature. So for Rust Lightning, this specific invoice, it has a invalid signature, but for core lightning it's fine. So this, I will talk more about this specific case in the next slides. So here it's basically listed the 15 bugs. So we find it's basically in all Lightning implementations, so LND, Core Lightning, Eclair, the Lightning KMP library, and so on. So this specific case is related to the high S and low S signature, since in the invoice we have the signature inside it. So basically in Rust Lightning, it was requiring just low S signature. So I basically created a pull request in the boat to formalize how we should handle signatures in the boat level invoice. So basically, when you start validating the signature in the invoice, you just look first if there is any field present, which is basically a public key. So in the spec says if there is a public key inside the invoice, we should verify the signature with the public key and with the data inside the boat level invoice. So by verifying, using the function verifying the signature, it's basically require low S signature, so it needs to be low S, but when it's missing the any field, we use another strategy which is recover the public key from the signature. So use the message and the signature to recover the public key, and that's basically verify the signature because we are getting the public key from the signature and the message data and the invoice data. So this one doesn't require the signature to be high, to be low S. So what was happening, it's basically Rust Lightning when doing this recovery, it was doing also a verify signature. That's actually, we don't need to do that again because we already verified the signature calling the recovery public key. So yeah, that's why they diverge in that specific input. So another example is Core Lightning was accepting some invalid invoice because in the boot level you have routing rings, and there we have a public key, and it was accepting invalid public key format. So basically, by doing differential fuzz, we could find this one. And sometimes by doing differential fuzzing, we are actually just fuzzing implementation that doesn't do fuzzing. So for example, Lightning KMP, which is a Kotlin library, don't do fuzzing. And so we could find a bug that just fuzzing would find by doing fuzzing. So in this specific case, in the Lightning KMP library, there is a TLV format in the Lightning, which is basically type, length, and value. And Lightning KMP wasn't verifying the length before it allocates the length, so I could pass length to be more than 4 gigabytes, and it would try to allocate that. So just doing thresholds, you could find this bug. How to contribute to Bitcoin Fuzz? So currently in Bitcoin Fuzz, it would be nice to adding new targets. There is someone working on BP32 key derivation, so we could have Bitcoin Core, BP32 key derivation comparing with the other libraries, and SecP 256K one, we could have, I don't know, verifying a signature with comparing with other SecP libraries. There are one written in Go, there are others written in C, which is the most famous one. And to be nice, add a new library, so both 11JS, which is using a lot in some Lightning wallets, BitcoinJ, which is a Java node implementation, and LibBitcoin, which is another one. Some build system improvements. So currently in Bitcoin Fuzz we have just a bunch of makefile to make it works. So we need to compile each module separately, and then we generate the final binary and execute the code, but it can be improve it a lot. And another one is just run Bitcoin fuzz and share the corpus generated by the fuzzer in the corpora, which we have in the Bitcoin fuzz organization. So we have a repository to basically just commit the corpus we have there. And that's basically it. Thank you. So, yeah, any question?
Hi.
Hi.
First of all, thank you for your work. It's super valuable to the broader Bitcoin and Lightning community, so thank you for that. Maybe I misunderstood, but you seem to hook in directly into the functions and not into the API calls,
Yeah,
correct?
yeah.
So that way you might miss some input sanitization that would happen in the different implementations that would lead to either maybe introduce new errors that you don't find, or maybe...
Yeah, we basically just take the function. We don't do like RPC calls or anything like that. There is one implementation to Bitcoin Core that does like fuzzing, but not differential fuzz in more high level, which is the fuzzamoto. So they actually send RPC calls and use the like send P2P message. But when doing differential fuzzing, we basically hook in those functions, and we don't actually can save states and like make it database call database function. So yeah, it's more stateless and easy to replicate.
Thank you. Thank you.
You're welcome.
Any more questions? No, we're done. Thank you.
Thanks.